Oftentimes, rocket scientists need to express the path of a rocket as a function of time, and yet still use x and y to describe the position. Therefore, they need to use parametric equations to link x and y with t for time. Hi, my name is Tom Atwater, and that's what we'll be looking at in today's lesson, parametric equations. Let's start with a definition of a relation. A relation is a set of ordered pairs, x comma y, of real numbers. The graph of a relation is the set of points in the plane that correspond to the ordered pairs in the relation. Now, sometimes x and y are functions of a third variable t, which is called a parameter. Let's look at that definition. Parametric curves and parametric equations. If x and y are given as functions, x equals f of t and y equals g of t, over an interval of t values, then the set of points x comma y are equal to f of t comma g of t, defined by these equations is a parametric curve. The equations are parametric equations of the curve. Let's try an example of using parametric equations. Given x equals t, y equals 1 minus t for the interval of 0 to t, the interval from 0 to 1 inclusive, graph the curve and answer what are the initial and terminal points, indicate where the curve is being traced from what direction, and then find the Cartesian equation for the curve that contains the parametricized curve. What portion of the Cartesian equation is then traced by that curve? Here's our graph as done on our graphing calculator. You can see that it's in the interval from 0 to 1, and we've graphed that x is equal to t and y is equal to 1 minus t. All right, the initial point would be right here at 0, comma 1. The terminal point is 1, comma 0, and that's the direction in which the graph is traced. The Cartesian equation for this would be y is equal to negative x plus 1. All right, some relations have parametrizations that can be standardized, and we're going to look at two of these. Let's start by looking at the circle. A parametrization of x equals a times cosine t and y equals a sine t is a parametrization of a circle with a center at 0, 0 and with a radius of a. Now, we could prove that by showing that the equation for a circle, which we all know is x squared plus y squared equals the radius squared, and in this case, our radius is a squared, we could simply plug in a cosine t for x and a sine t for y, and then when we square each of those, we would get a squared cosine squared t plus a squared sine squared t. And that equals a squared. Now, if we factor out the a from there, you'll notice that you're left with cosine squared plus sine squared. And from your trig identities, you know that cosine squared plus sine squared is equal to 1, which means we have a squared equals a squared. All right, let's look at an example of using this parametrization. Given that x is equal to cosine t, y is equal to sine t in the interval from 0 to pi inclusive, graph the curve. What are the initial and terminal points? Indicate the direction that the curve is traced. Part B, find the Cartesian equation for a curve that contains the parametrized curves. what portion of the Cartesian equation is traced by the parametricized curves? All right, so let's take a look at this on the graphing calculator. What we can see is that the initial point is 1, 0. It is traced in that direction to the terminal point of -1, 0. This, of course, is the graph of a circle. And therefore, the equation, it's just going to be the top half. So the equation is y equals the square root of 1 minus x squared. And that would be our Cartesian equation. And again, the restrictions are from -1, 0 to 1, 0. Now, the other standard parametrization we want to look at is one for an ellipse. So, a parametrization of x equals a cosine t, y equals b sine t. So notice there's a difference with the circle in that we have a b introduced on the y. And this is a parametrization of the ellipse, which has a center of 0, 0. So let's try an example of this. Given that x is equal to 4 sine t and y is equal to 2 cosine t on the interval from 0 to pi, graph the curve. What are the initial and terminal points? Indicate the direction that the curve is traced. Then find the Cartesian equation for a curve that contains the parametricized curve, and what portion of the Cartesian equation is traced. Okay, so once again, we turn to our graphing calculator when we see that this is the curve which shows us the right-hand side of the ellipse. Now, the initial point is up here at 0, 2. And it gets traced in this direction all the way to the terminal point, which is 0, -2. Now, the equation would look like this. X over 4, quantity squared, plus y over 2, quantity squared, is equal to 1. But again, we're only interested in the right-hand side, so that would be for x greater than or equal to 0. Now, that's one form of the equation, but we're interested in only the right-hand side, so what I'm going to do is write out what that equation would look like. And in that case, what we would have is x equals 2 times the square root of 4 minus y squared. And in that case, we would take all of that equation because it does represent only the right-hand side. Great. Now, let's try some other examples that are not necessarily circles or ellipses. Let's take, for example, that x is equal to 2t minus 5 and y is equal to 4t minus 7 on the interval from -infinity to infinity. Graph the curve. What are the initial and terminal points? Indicate the direction in which the curve is traced. And finally, find the Cartesian equation for the curve that contains the parametrized curve and what portion of the Cartesian equation is traced by it. So let's take a look at that graph. We have the graph of a straight line. The interval, remember, was from -infinity to +infinity, which means there is no initial point, and there is no terminal point either. The equation for this would be in the slope-intercept form, y equals 2x plus 3. And that would be the linear equation, and all of it is traced because, once again, we had an interval from -infinity up to positive infinity. Now, let's find a parametrization for a curve given as a Cartesian equation. In other words, let's go in the reverse direction. Find a parametrization for the lower half of the parabola x minus 1 equals y squared. So what I will give to you are the fact that you've got to start with something like, for example, let's say that we're going to put y equals t. Okay. Now, using that y equals t, we would say that x is going to be equal to t squared plus 1 with the restriction that t is less than or equal to 0 because we're interested in the lower half of that parabola. So that would be a parametrization of x minus 1 equals y squared. Well, now it's time for you to try a problem. So let me show you the problem that I would like you to do, which is find a parametrization for the ray with the initial point 2, 3 that passes through the point -1, -1. So pause the video while you work on this problem, and when you're finished, restart the video to check your solution. There are many answers that could work for this, and I'm going to show you one possible answer. You could use x is equal to 2 minus 3t, and if you do that, then y is going to have to be equal to 3 minus 4t. And in this particular case, we would have t greater than or equal to 0. So that would be finding the parametrization from the Cartesian information. Okay, so great. In this lesson, we learned about parametric curves, parametric equations. Be sure to work the exercises that your teacher assigns, and we'll see you next time.